today's lesson is going to be focusing on convolution. And you'll remember how to do convolution, or you'll remember vaguely about convolution from signals and systems. It turns out that in discrete time, it's easier. And we're going to handle it by math, and we're going to start off deriving the math with intuition. It's actually intuitive in discrete time. And then we'll talk about some properties of convolution. And then we'll talk about how to do it with MATLAB. And then the granddaddy of all, we're going to talk about how to do it graphically, which is the trickiest part. And that, much like last night's homework assignment, is going to just require a lot of practice to get down. Let me dive right into it about convolution. Convolution is a way that, assuming you know what the impulse response of your system is, which is just a description of your system, it's what it does to an impulse, you can find the output directly. And we did this in continuous time when we said x of t convolved with h of t. And that was that nasty integral is equal to y of t. But you know, unlike the continuous time, this actually makes sense. Let's say you have an input, an x of n. And it's zeros everywhere. Except for this. And everything else is zeros. All right, so this is 0, 1, 2. We can break this input up into a sum of impulses, where the first is an impulse that triggers at 0. And the second is twice times an impulse that triggers at n equals 1. And then the third is an impulse that triggers at n equals 2. So each of these guys are not a number. This, it's not a function. That's a number. That's equal to 1. But the below is but these are functions. And so if we add these functions up, we get our original input. So you know, if our system is linear, that this, an impulse in, by definition, creates what as an output?
What do you mean by creates what as an output?
If you have an input, an impulse in to a system, by definition, what is the response of a system to an impulse in?
Oh, it's a finite set of...
That's true, but it has a name. Don't overthink this. What is the response to an impulse in? Impulse goes into your system, and so the system's response is called a impulse response. H of n. If you put an impulse in, by definition, what you get out is the impulse response, h of n. But this is just an impulse that's been delayed by 1 and multiplied by 2. And this is just an impulse that's been delayed by 2. So this should give an impulse response delayed by 2. Right? Because if you know that an impulse in gives you an impulse response out, then a delayed impulse in should give you a delayed impulse response out, and so on for an impulse in delayed by 2. And if by linearity, we know if we multiply one of these guys by 2, the output is just multiplied by 2. And so there you've got your output. That's just convolution. So in general, if this is true, if the above is true, then y of n is going to be, I hope you can see that this is scaling. We've got an h that's just, we're going to have to do summations, right? And we're going to have to do our summation, say, with a new dummy variable. And it's always going to have the form of n minus some shift. So that's the h here. And then it's going to be multiplied by some coefficient over here, which is just whatever our input is at that location. So this is the formula for convolution. Now convolution, the formula works in reverse too. So we can flip our roles of x and h and have it still work. But it's really the first one that you see the most of the time. And this is just the same notationally as saying it's x convolved with h. And you've seen this before. I mean, compare this with, in continuous time, y of t, which is minus infinity to positive infinity. We're going to let tau range in that range of x of tau, h of t minus tau. Whoops, I'm drawing the square brackets automatically. So if you take a look at this, compare it to this, it's the same exact thing. We're just replacing a summation formula with an integral formula. This is what convolution is, and we just derived it from intuition. And the gotcha with all this has to do with notations. So convolution, the rest of the world uses this symbol for convolution, just like we did. Mitra, to avoid confusion with a topic that we will incredibly briefly cover for one fraction of a class, uses a separate symbol for convolution. We're going to use what everybody in the world does. And then there's this thing, this is the topic that occurs very, very briefly. Circular convolution. So everyone in the world uses the convolution operator with a circle around it to denote circular convolution. But Mitra comes up with his own notation. And there's a reason for it, but it's not worth getting into. We're going to use what the rest of the world does. And then don't confuse that with conjugation, complex conjugation, which is also a little asterisk. Mitra also uses a little asterisk, but that's when you're saying this convolution, say, of 2 at an angle of 3 is equal to 2 at an angle of -3 degrees, or 2 plus j conjugated is 2 minus j. Okay, questions about the notation? We're going to use regular convolution. I'm just letting you know that Mitra has this other weird symbol, but there's not going to be any confusion. It's clear from context that he's talking about convolution.